There's lots of examples where equilibrium comes into place. Reactions that don't go to completion because they're reversible. Weak acids, weak bases, buffers. Another example is when you take a salt or something, you throw it in water and it only partially dissolves. For example, if you take some silver chloride and you throw it in water, you'll get some silver ions, you'll get some chloride ions, but you'll also get a lot of undissociated silver chloride. This makes it a reversible process. This makes it an equilibrium situation. And as you might guess, we have an equilibrium constant that goes along with it. We define this as the solubility product constant since it's going to be equal. If we take a look at this from a pure equilibrium situation, just like we've done before, K is going to be equal to concentration of the products over the reactants. We're going to omit the reactant since it's not in solution, it's undissolved, it's a precipitate. It didn't precipitate out of solution, it just never went into solution. And so all it is the concentration of each ions where you have the coefficients becoming the exponents. In this case, they're both 1. We have a special name for it, not just K, but Ksp. The solubility equilibrium, the solubility product constant. These do get multiplied by each other, and there will be exponents that come into play, so let's take a good look at it. This will be some number which you can look up in a table. You could look up the solubility product constant of silver chloride, and since it's a 1-to-1 ratio, we should be able to, from that, come up with the concentration of each ion. It's the table's listed at 25 degrees Celsius molar concentrations. And for silver chloride, it's 1.26 times 10 to the minus fifth is not the Ksp, that's the concentration of each ion in solution, S, if you will. It's this number for this, and since it's dissociating, it's going to form equal amounts of that. That's the concentration of silver plus, and that's the concentration of chloride minus. So Ksp will just be that number squared, S squared if you will, and it's 1.6 times 10 to the minus 10th. So the reverse thing would be if you're given the Ksp, you could say, well, the concentration of each ion must be that, because you're going to take the square root of each one for this simple 1-to-1 ratio kind of system. Now, if we have something that's not a 1-to-1 situation like magnesium fluoride, the math just comes out a little bit different. By the way, why are they doing this crazy multiplying thing? Why don't they just tell you the solubility in moles per liter, or even better, grams per liter, or maybe even percent by mass? You could do that, and people use those numbers all the time. The advantage of this system is it parses it out into each ion. So if we added a little, say, silver nitrate to this solution, it could precipitate out silver chloride, since this won't change, but this will change. So it's a more sophisticated way of looking into it. Take magnesium fluoride, throw it in water. You'll get some magnesium cations, some fluoride anions, and you'll also get some undissolved magnesium fluoride. It's a slightly soluble salt. In this case, for every magnesium ion that forms, we get twice as many fluoride ions, so this is going to affect things mathematically. But we don't have to get too predictive about it. We can do our standard analysis. K will be equal to the concentration of products over reactants, like we always do. Coefficients become exponents, that's fine. You look it up and you find that that's the number. Could you figure out what the concentration of magnesium ion is and fluoride ion is? Well, I think you could, but don't forget there's going to be twice as many fluoride ions as magnesium ions, so we'll have to look at this in more detail. Before we go any further, why did we eliminate the denominator? We mentioned it here before. It's not in solution. It never got dissolved, and therefore it gets omitted from the calculation. All right, and sometimes you get situations where somebody tells you how much is in solution, and you can compare that to Ksp to see if things are okay or if they're a little bit off. Q is the measured equilibrium. If it's less than the equilibrium constant, that means more could go into solution, and the equilibrium will shift to the left. It's not even up to how much it can handle. If it's exactly the same, that means this reaction is at equilibrium. Don't say that it's stopped, but the rate of the forward reaction is the rate of the reverse reaction. And if it's greater than that, that can happen temporarily, but that's a supersaturated situation. It's going to shift to the left, and you're going to get some precipitate. So when it's less, it's unsaturated, not yet saturated. When it's equal, it's saturated. When Q is higher than the Ksp, it's a supersaturated solution. Finally, let's take a look at how we can mathematically relate Ksp to the concentrations of each ion, which we could call S. Basically, we can call it S. It doesn't account for the fact that 2-to-1 ratio here, but take a look at it. You'll see what we see. Silver chloride, which we just did. Ksp is equal to this times this, fine. The cation we will call S, the anion we will call S, and so Ksp is equal to S times S, that's X squared, S squared. And therefore, S will be the square root of the Ksp. That will tell you what that value is. And in this case, it is the concentration because it's a 1-to-1 ratio. What about barium sulfate? Oh, they're 2 plus and 2 minus. Are things any different? No. It's exactly the same situation, right? Is this showing up? There it is. Exactly the same situation, 1-to-1 ions. Ksp is the square root of S is equal to the Ksp square root. Silver 1 carbonate. Silver's always plus 1. Ksp in this case will be equal to the concentration of silver times the concentration of carbonate, but what did I forget? Coefficients become exponents, so it's squared. The cation is going to be twice as high as the anion, so let's call that 2s and the anion s. What's the relationship between Ksp and S? Let's see. It must be 2s. We can plug it in right there. 2s quantity squared times S. A lot of people mess this up. 2s quantity squared is not 2s squared. 2s quantity squared is 4s squared. And 4s squared times S equals 4s cubed. So that's how you're going to get Ksp from S. We can't call S the concentrations because 2s is the concentration of the cation. We're just going to call it S. And if that is true, we could take the cube root of 1/4 of the Ksp to find out S. Makes sense? They just did a mathematical rearrangement. They're going to go even higher. In fact, they're going to go up to a 5-fold system. So a lot of times AP students are really good at this because they're solid at the math. So try to predict each blank here. PbF2. How can we write the Ksp expression? Well, it must be lead times the concentration of fluoride ion squared. Therefore, the cation in this case is just S, and the anion becomes 2s. Same situation, it just turned out mathematically the anion versus the cation, same answer. Aluminum hydroxide, wow, 3 hydroxides per aluminum, so it'll be equal to the concentration of aluminum times the concentration of the hydroxide to the 3rd power. Good. And we can call S the cation, but we better call 3s the concentration of the anion, since we'll have 3 of these built in to every one of those. I clicked this already, but I bet some of you would have been able to do that. 3s quantity cubed becomes 27s cubed multiplied by S becomes 27s to the 4th. Rearranging it, I'm not even going to say what that is because it's hard to express it, but there it is. And finally, a 5-fold system. Go ahead and fill in these rows, or at least just think about it as I do it and see if you get the same answer. Let's see, it must be equal to the concentration of the calcium ion cubed times the phosphate ion squared. Yep. We can call this 3s, and we can call that 2s. That wasn't too hard. But what the heck would this be? Oh my god. 3s quantity squared is equal to 9s squared, is it not? 2s, no, it's cubed, isn't it? 3s quantity cubed is equal to 27s cubed multiplied by, yikes, 4s squared. That sounded like 27 times 4, 54. It's 108s to the 5th. And the S value would be equal to the 5th root of 108th of the Ksp value. And it rarely goes up that high. But that's how we can relate S to Ksp, how we can relate Q to Ksp, and how we can understand solubility, equilibrium in general.